am Dr. Ramanuja, working as an associate professor in Department of Mathematics, Marri Laxman Reddy Institute of Technology, Management and Dundigal. In the previous classes, I discussed about mean value theorems. One is Cauchy's mean value theorem, Rolle's theorem, and also Lagrange's mean value theorem and their geometrical interpretation and their example problems also. Previous class I discussed. Today's class we are going to discuss about expansions of functions using Taylor's theorem and as well as Maclaurin's series. In this 3.1 module I covered 3.1 module I covered, 3.2 module also I covered, 3.3 module also I covered. Now I am in 3.4 module, which is Taylor series. In this Taylor series, the statement of the Taylor's theorem, just let me go with the theorems, then I can go with one more part, problematic. Today I am going to discuss about only Taylor's theorem and also the statement of the Taylor's theorem. What are the remainders, Taylor's remainder and Maclaurin's remainder, Cauchy's, Lagrange's mean value remainders also. Okay, let us go with the Taylor's theorem. This Taylor's theorem statement that f is a function mapping from a b to r. F is a function defined from a b to r such that f power n minus 1 derivatives always continuous in the closed interval a comma b, and also f power n minus 1 terms differentiable in the open interval a comma b, then there exists a f power n value, in between open interval a comma b such that there exists a point c between a and b if you expand f of x equal to f of a plus x minus a by 1 factorial into f dash of a plus x minus a whole square by 2 factorial into f double dash of a plus so on x minus a whole power n minus 1 divided by n factorial into f power n minus 1 into a. But this is about the statement of Taylor's theorem. Further, I am extending the Taylor's theorem in the form of Maclaurin series. See, in the Maclaurin's theorem, the statement of the Maclaurin's theorem, f is a function defined from the closed interval 0 comma x. We started initial conditions from 0 to x, x from where to where, x to r, real number system, and also similarly like a Taylor's theorem, f power n minus 1 derivatives always continuous in the closed interval 0 comma x, and also second condition f power n minus 1 is differentiable in the open interval 0 comma x. Then there exists f dash, then there exists f power n exists in between the open interval 0 comma x such that c between a and b f dash of x equal to f of a f of 0 plus x by 1 factorial into f dash of 0 plus x square by 2 factorial into f double dash of 0 plus so on x power n minus 1 into n minus 1 factorial f power n minus 1 into 0. This Maclaurin's theorem. Here we started expansions of the function from the point 0. Okay. Further, I am going to give one series. For that series, how do you existence of the Taylor's theorem? How do you existence of the Maclaurin series? Okay. Let us take. Let us go with the remainders, Taylor's theorem with Lagrange's remainder forms. Let us take the first one. It shows that the Lagrange's mean value theorem, Taylor's theorem with Lagrange's form of the remainder. Here f of x plus h equal to x f of x plus h by 1 factorial into f dash of x, h square by 2 factorial into f double dash of x, h cube by 3 factorial into f triple dash of x plus so on h power n minus 1 by n minus 1 into f power n minus 1 of x into their remainder values. Okay, what is the remainder now? Lagrange's remainder in this case, h power n by n factorial into f of x plus theta into h. This is Taylor's theorem in the form of Lagrange's remainder. Similarly, Taylor's theorem with the Cauchy's form of the remainder. Similar expansion f of x plus h, if I expand their h power n minus 1, which is their Cauchy's remainder is Rn. Rn is nothing but h power n by n factorial 1 minus theta whole power n minus 1 f of x plus theta into h. This is about the Taylor's theorem in the form of Cauchy's remainder. Similarly, Maclaurin's theorem in the form of Cauchy's remainder. Let us take Maclaurin series f of x equal to f of 0, x by 1 factor into f dash of 0, x square by 2 factor into f double dash of 0, x cube by 3 factor into f triple dash of 0, plus so on x power n minus 1 by n factorial into f power n minus 1 of 0, plus we are adding some remainder values. Then the Lagrange's form of the remainder is x power n by n factorial into f power n into x comma theta, where theta value lies between 0 and 1 values. Okay, these are the Taylor's theorem in the form of Lagrange's remainder as well as the Cauchy's remainder. Maclaurin's theorem in the form of Lagrange's remainder. Let us go with the how these series are expansions. Why do you expand all the functions? If you expand any function, we need to calculate at the particular point what is the behavior of that particular function. This is the main motive of this expansion. Let us go with the first condition. Are you observing? I think first condition. What is the first condition? Shows f of x plus h equal to f of x plus h by 1 factorial into f dash of x, h square by 2 factorial into f double dash of x, plus h cube by 3 factorial into f triple dash of x, plus so on up to infinite terms. These are the expansions of the any function in the form of some difference values of h we expanded. For this function, we need to convert into Taylor's series. We need to convert what? Taylor's series. See the equation 1. Let us assume this is equation 1. Equation 1, we need to substitute x is replaced by a. Let us assume in the equation 1. I am going to substitute. Let us substitute, put x is equal to a, and I am going to substitute h by x minus a. H is replaced by x minus a. What happens? The series becomes f of x. Now this becomes what? F of x plus h. If I add x plus h, what happens? It remains f of x. What is x? X is nothing but what? F of a plus h. What is meant by h? X minus a. X minus a whole square, sorry, x minus a divided by 1 factorial into f dash of a plus x minus a whole square by 2 factorial into f double dash of a plus x minus a whole cube by 3 factorial into f triple dash of a plus so on up to infinite terms. Now we got this series. This series is nothing but what? Taylor's series. How do you derive this series? Are you observing the first equation? First equation is what? F of x plus h equal to f of x, h by 1 factorial into f dash of x, h square by 2 factorial into f double dash of x, h cube by 3 factorial into f triple dash of x. What I replaced now? I replaced x by a and h by x minus a. This is nothing but what? What kind of the series? This series is called Taylor series. This series is called as Taylor's series at the particular point of x equal to a. At the particular point of x equal to a. Let us come with the, this is the second condition. Now I am going to take the equation 1 similarly. Equation 1, what is equation 1? F of x plus h, f of x, h by 1 factorial into f dash of x, h square by 2 factorial into f double dash of x, h cube by 3 factorial into f triple dash of x. For this series, I am going to substitute equation 1, x is replaced by 0. X is replaced by 0. Then x is replaced by 0 and h is equal to how much? I am going to substitute x in the equation 1. For this equation, I am going to substitute how much? X value is 0. H is replaced by what? X. Then this equation becomes, what happened? This equation, first equation becomes f of x. What is x? X equal to how much? 0. Then it becomes what? F of 0 plus h. H is nothing but what? X by 1 factorial into f dash of x value 0 plus x square by 2 factorial into f double dash of 0 plus x cube by 3 factorial into f triple dash of 0 plus so on up to infinite series. Now we find the expansion at the function at where we find at the point of 0. At this point of 0 is called Maclaurin series. Maclaurin's series. Now we taken this function, we taken the first equation. What are the substitutions we made? What are the substitutions we made? For this equation, I substituted at the particular point of A, I expanded, then h is replaced by x minus a, this becomes Taylor series. Now similarly, the equation 1, I substituted at the particular point x equal to 0 and h is replaced by x, this becomes Maclaurin series. Now clear about the Taylor series as well as the Maclaurin series for these functions. Okay. Let us go with one example problem. How do you expand the functions? How do you expand the functions in the form of Taylor series of the functions? Let us go with the example problems. How do you expand the functions which is in the form of whether it is a fractional values or rational functions? Let us go some example problem. How do you expand the previously we studied the some expansions of the function. Let us take the basic expansions of the Taylor's basic expansions of the Maclaurin's expansions of the function. Where do you expand Maclaurin series? At the particular point x equal to 0. We know 1 by 1 minus x. How do you write this function now? I think you familiarized by binomial expansions and all rational index values. This is nothing but 1 minus x whole power minus 1. Now this rational index function we expanded in the form of what? 1 plus x square plus x cube plus so on. This is a sigma, I can say n equal to 1 to infinity expansions of x power n. Let us take one more function you familiarized by e power x value. What is e power x? 1 plus x by 1 factorial, x square by 2 factorial, x cube by 3 factorial plus so on up to infinity sigma n equal to 1 to infinity x power n by n factorial. This also an Maclaurin's expansions of at the point x equal to 0. Let us take one more. These are the general functions of Maclaurin series. You familiarized by the trigonometry function which is sin x. How do you get the sin x expansions? You know, okay, at the particular point x equal to 0, therefore x minus x cube by 3 factorial plus x power 5 by 5 factorial, x power 7 by 7 factorial plus so on. These are all we can expand by using the Maclaurin series function at the point x equal to 0. Similarly, we take the function cos x defined at the particular point x equal to 0, this becomes 1 minus x square by 2 factorial, x power 4 by 4 factorial minus x power 6 by 6 factorial plus so on. I can write in terms of sigma notation. And also log of 1 plus x can be expanded at the particular point x equal to 0. The expansion is 1 minus x square by 2 plus x cube by 3 minus x power 4 plus so on up to infinite. These are the basic expansions of the function. These functions are we can expand at the particular point using the Maclaurin series. Let us go with some example problems today's class. Okay, the problem number 1 is Taylor's theorem. We are applying Taylor's for this function. Why we to apply the Taylor's theorem? Already I told in the previous series how do you get the expansion of the function. This is the basic function. For this basic function, we substituted x by what? A and h by x minus a. We expanded this function at the particular point x equal to a. This is the main concept of expansions of the Taylor series of the function. Let us take this function. Obtain the Taylor's expansion of sin x in the powers of what? X equal to pi by 4. We need to expand this function at the particular point x equal to pi by 4. This represents a Taylor's series. Okay, let me write the Taylor series expansion first, then I can expand this function. Okay, let the Taylor's expansion at the point x equal to a. What happens? F of x, f of a plus x minus a by 1 factorial into f dash of a plus x minus a whole square by 2 factorial into f double dash of a plus x minus a whole cube by 3 factorial into f triple dash of a plus x minus a whole power 4 by 4 factorial into f fourth derivative of x plus so on up to infinitum. These are the Taylor's expansion at the particular point x equal to pi by 4. What is a given function? What is a given function? Let f of x equal to what? Sin x. F of x equal to sin x. We need to calculate first f of a value. What is a in this case? At a particular point what? A equal to how much? Pi by 4. For this function, we need to calculate f of pi by 4, sin pi by 4. What is sin pi by 4? Pi by 4 is nothing but 45 degrees, which is nothing but 1 by root 2. Similarly, we need to calculate f dash of x. What is the derivative of sin x? Derivative of sin x equal to how much? Cos x. Then we substituted f dash of pi by 4, which is equal to cos pi by 4. What is cos pi by 4? 1 by root 2. Cos pi by 4 is 1 by root 2. Similarly, f double dash of x, when we calculate the second derivative, derivative of cos x is how much? Minus sin x. That implies f double dash of pi by 4 is equal to minus sin pi by 4, which is equal to minus 1 by root 2. Similarly, we can calculate the third derivative of this function, sin x derivative. It become already there is a minus, sin derivative is cos x. When we calculate f triple dash of pi by 4, f triple dash of pi by 4, which is equal to minus cos pi by 4, which is minus 1 by root 2. Similarly, we calculate the fourth order derivative of this function, cos derivative is, it becomes minus sin. Already there is a minus, it becomes what? Sin x. That implies f fourth derivative of pi by 4 is equal to sin pi by 4, which is 1 by root 2. Now, we are going to substitute first f of a value, f dash of a value, f double dash of a value, f triple dash, f our fourth derivative, and a is replaced by how much? Pi by 4. Now, this expansion becomes f of x is equal to f of a how much? 1 by root 2 plus x minus a is how much? Pi by 4 whole divided by 1 factorial into f dash of a. F dash of a value how much we got? F dash a value, f dash of a value how much I got? 1 by root 2. Now, I am going to substitute 1 by root 2 plus x minus pi by 4, x minus pi by 4 whole square by 2 factorial into f double dash of this function, which is minus 1 by root 2 plus x minus pi by 4 whole cube divided by 3 factorial into f triple dash of this value is how much? F triple dash of value minus 1 by root 2 plus x minus pi by 4 whole power 4 by 4 factorial into f power 4th of a, how much? 1 by root 2 plus so on up to infinity. Now, look, this is the expansion f of x we got. We expanded at the particular point of x equal to pi by 4. For this expansion, wherever we see the powers of pi by 4, look, this first one is x minus pi by 4 by 1 factorial power. What is the second power? X minus pi by 4 by 2 factorial and x minus pi by 4 whole power 3 by 3 factorial, x minus pi by 4 by 4 factorial plus so on infinite. Further, if I simplify this, I am going to remove this negative sign, I am going to remove this negative sign. I can rewrite this function f of x is equal to 1 by root 2 x minus pi by 4 into x minus pi by 4 into 1 by root 2. There is a minus, therefore, minus of x minus pi by 4 by 2 factorial into 1 by root 2 minus 1 by minus x minus pi by 4 by 3 factorial into 1 by root 2 plus x minus pi by 4 into whole power 4 by 4 factorial into 1 by root 2 plus so on infinity. Just I interchanged the negative sign. Here is there is a negative, here is there is a negative. Now this becomes what? Expansions of Taylor's function at the particular point of x equal to pi by 4. We can expand this function at the particular point of x equal to 0. Instead of x is replaced by 0, it becomes Maclaurin series. In this series, I can substitute x wherever x is there, pi by 4. This becomes a is 0. In this case, this series becomes what? Maclaurin series. Okay. Further, we can expand similarly. We can expand sin x. We can expand sin x. Even in the values of, we can substitute x at the particular point of pi by 2, or we can take pi by 6. Similar function. Even you can take cos x, also similarly pi by 4 we can expand, pi by 2 also we can expand, pi by 6. What is the use of this studying the expansion of this function? We can observe the behavior of this function at the particular values. Wherever you need that particular value, we can substitute. Excuse me. Right, one more function I am going to explain. This simple function, for this class I am going to take very a simple function only for the Taylor's expansion of the function. Obtain the Taylor's expansion of the function e power x about the point x minus 1. We need, wherever we expand this function, in the forms of what? X minus 1. Now I am going to write the Taylor's expansion first. What is Taylor's expansions? Taylor series. What is Taylor series? F of x plus f of x equal to f of a plus x minus a into f dash of a plus x minus a whole square by 2 factorial into f double dash of a plus x minus a whole cube by 3 factorial into f triple dash of a plus so on up to infinity. Now, where this function can be expanded at the particular point of what? X minus 1. We need to write the Taylor's expansion in the powers of x minus 1. Let us assume this function x minus 1 equal to 0, x equal to 1. We need to expand this function at the particular point of 1. We can expand x equal to at the particular point of, if I expand x equal to 0, if I say this is nothing but a Maclaurin series. That is the difference between Taylor's and Maclaurin series. Now this x equal to 1 represent what? Now what is the value of a now? X equal, what is a value? A value becomes how much? 1 now in this case. Okay, let us take the function. What is the function is given? E power x. F of x equal to what? E power x. Now we need to calculate f of a value. We need to calculate what? F dash of a value. We need to calculate f double dash of a. We need to calculate f triple dash of a for these functions. Okay, let us calculate f of a value. F of a value means what? Just we are going to substitute a is replaced by 1, which is nothing but e power 1 is e. Similarly, we need to calculate f dash of x. What is the derivative of e power x? E power x. That implies f of 1 equal to e power 1, f of 1 equal to e power 1, which is equal to e. Similarly, we need to calculate f double dash of x, which is e power x, because the derivative of exponential function e power x, always derivative is e power x. Just we are going to replace a value, that's all. F dash of 1 is also same. F double dash of 1, which is e power 1, which is equal to e, and f triple dash of x is equal to e power x. That implies f triple dash of 1 is equal to e power 1. This also the same e. Now I am going to substitute this function f of x, f of a, how much I got? E plus x minus a value is how much? 1 into f dash of a value is how much? E plus x minus 1 whole square by 2 factorial into f double dash of a e plus x minus 1 whole cube divided by 3 factorial into e plus so on up to infinite term. What is the common for this expansion? F of x is equal to e is common 1 plus x minus 1 plus x minus 1 whole square by 2 factorial plus x minus 1 whole cube by 3 factorial plus so on infinity. This is the expansion of e power x at the particular point x equal to 1. Okay. Now, these are the basic expansion functions. We discuss in this class only Taylor's series, but for both the function, whatever I take an trigonometry function. Even this exponential function also, we can expand for this function at the particular point x minus 2, or see now this powers in the form of what, x minus 1 whole square. This is the behavior of the function e power x at the particular point x equal to 1, even though you can expand x equal to 2, x equal to 3, x equal to 4 for this function. And also wherever we substituted suppose x equal to 0, suppose this function I expanded at x equal to 0, same series we are going to, same derivative we are going to calculate, only series will be diverse at the particular point of what, if I say at the particular point x equal to 0 is called as a Maclaurin series. In the next class I am going to discuss about the Maclaurin series expansions of the functions. Okay, example problem I will discuss. Okay, thank you.